All right, good afternoon, everyone. My name is Hoang Nguyen. I'm a senior in the biomedical engineering program here at San Jose State. This is my partner.
I'm Hazim Amir. I'm a senior in the biomedical engineering program at San Jose State University. Our project is novel introducer sheath for catheters. Our advisors are Selvaduray at Zandi, and our project sponsored by Implant Solution.
So this is a brief outline of what we'll be talking about. So we have the biomedical motivation, various catheterization procedure. We talk about the FDA consideration of this device, and go toward the method, the testing, and the preliminary results that we have.
So starting with motivation for the project, cardiovascular diseases are behind 30% of global mortality. The standard treatment for cardiovascular diseases is open heart surgery. As we can see, it's very invasive. It requires to open up the chest to reach to the affected area. It's mostly effective in senior over 65 and infant with heart defects. So an alternative to open heart surgeries is catheterization. And catheterization is minimally invasive. It composes of few simple parts. I'm going to pass this around. Please don't open it. And I have one open that I'll do a demo to give you an idea what catheterization is. So there is a needle that the surgeon uses first to access one of the big arteries in the body, such as femoral artery. So the needle goes in first, and then there's a guide wire that goes from the back through the needle. And then after that, the sheath and the dilator goes together over the guide wire. Well, before they insert that, they remove the needle. So this is inside the blood vessel. And then there is a center hole here, so they go over the guide wire again. And then inside the blood vessel. And once both of them are inside, they take the dilator out. The dilator is a more rigid material, more rigid polymer, and this is more flexible. So once both of them are inside, they take the guide wire, they take the dilator, and they leave the sheath inside the blood vessel for catheters to go in. And that's our project, the sheath.
Typically, what you see right now, the catheter sheath tend to have a fixed diameter, so it's just one size, fit only one size catheter. And each of these catheters, let's say if a doctor wants to switch out another catheter, another incision has to be made because the other catheter may have a different size, which may only fit certain size catheter sheath, so they have to make another incision, which may lead to more problem later on. More incision means there are more chances of infections. And here's some picture of infection due to the incision made of a catheter. And these catheters, sometimes if you have a big sheath, it basically means you have to make a big incision. Once again, more chances for infection. So the FDA state that, well, this catheter sheath fall into the FDA class 2. Why? Because even though it goes inside the human body, but if it breaks, it doesn't cause any lethal damage to the person, right? If it breaks inside, you can do a surgery and take it out. Whereas if it fails, it won't kill, you won't die from the failure of the catheter sheath. And over the past 10 years, there have been about 273 recalls of the catheter sheath from various manufacturers, such as Boston Scientific and Edward Life Science. Mainly, most of the problems, the recalls were caused by because the sealing of that sheath, the bag was back, you know? Yeah, that sealing is very important, make it sterile. So sometimes the sealing may not be tight, and that leads to recall.
Yeah, also tube, liner, sometimes they use a liner inside the inner diameter. They put other material to make it more lubricious. Sometimes the liner come off, things like that. So these are the main objectives for our project, and this in conjunction with the company that we're working with. So the first two objectives is proprietary for the company that we're working with, and unfortunately we cannot show the design at this point because it's not patented yet. The rest are sort of general objectives for most catheter sheath on the market, such as buckling resistant, leakage resistant, bending, torsion, and lubricity. So we went through about 8 revisions of the design, and we're at the final stages to freeze the design. Some of the challenges that we encounter is the leakage, make the sheath leak resistant and does not cause any leakage when it's inserted in the blood vessel. That was one of the main challenges that we spent most of the time on. Also finding information about predicate devices, particularly on information on testing they've done, what the result they've gotten. Also making the sheath flexible at the same time, buckle resistant, like rigid and does not kink easily, and also manufacturability.
So there's always a trade-off. You want to expand the sheath to have certain features, but that features may not be possible due to the tool that needed to make the actual sheath. Mainly we make it through extrusion. That's the process we're looking at.
Yeah, so we went through complex design, then we went through assembler design to ensure that it's not only it does the job, but also it's manufacturable.
So with that, we went ahead and bought some predicate devices. We want to do the 3-point bend test and the 4-point bend test. This is one of the ASTM that we based off of. As you can see, the standard call for a 3-point bend test of another of vascular stent, but we modified it for a catheter sheath. This span length can be there's an equation for a certain size catheter sheath, and then we have to base off that and come up with a span length based on the equation inside the ASTM. There's a reason why we want to do the 4-point bend test, because right now, before this, the 3-point bend test only apply the load at one point, and most likely we will know that it will cause the most stress on that middle point. Instead, we want to opt for the 4-point bend test to have a better distribution of load over the span length. So therefore, we went ahead and have 2 different sheaths. Well, these are tubings. So, but P-backs, we got these from Zeus sample, and we have 2 diameter, inner diameter, 0.259 inches and 0.095. And what we did was we did a 3-point bend test and a 4-point bend test. We stop when there's the size of kinking, when there's a bend in the material. And this is mainly, we stop due to a visual check. We're not based on the data. So for each size catheter, each size tubing, different diameter, we do a 3-point bend test, a 4-point bend test. We compare it. The reason we're doing this is, once again, we want to validate that 4-point bend test, and from then on, continue doing the 4-point bend test rather than 3-point bend test. We look at the data, and it shows that on the same scale, it shows that the 4-point bend test shows that the sheath can actually handle more load, because it gives us a better idea, representation of what's going on.
And again, the 4-point bend test is a better representation of the actual load on the sheath, because in the operational room, it will be applied load from the hand of the surgeon, and it's going to be fixed from the bottom, so it's going to see 2 loads and not just 1 load in the middle.
And we did the same test for the smaller, so we scaled down the size of the catheter. And as we scale down the size, the difference became insignificant, because due to one of the problems is the loading, the load cells on the instrument machine is way too big compared to what the small sheath can handle. So it didn't give us really meaningful data for that, fortunately.
So one of the tests that we need to do is buckling test. So we designed a buckling fixture. As you can see here, we use the threaded rod that goes through bars, and we convert an rotational force to axial force, and the sheath will be placed here, and it's going to be fixed from the top and bottom. That's an adapter where the sheath goes in, and the sheath will be fixed from the bottom by these 4 screws. So basically, we turn the threaded rod from the top, and we apply force. And at the end, we're looking for signs of kinking. How to measure the force we're applying? We have a sensor at the bottom to measure the force applied on the sheath. And we will go over how to record the data as well. So before we go there, why we're doing buckling to ensure that the sheath that we're designing can withstand the axial forces that we'll encounter in the operation.
So for the little piece of device that you saw at the bottom, the FSR, the force sensitive resistor, by itself, on its own, it's just a resistor that can change the resistance when there's a force applied. And we will connect that to a data acquisition device, and set up a lab view virtual instrument. So this is the entire loop, and this is the data, the device. This will control the device to measure the resistance constantly, and then write down the resistance to an Excel. And as we press the force on it, the resistance will have to change. So right now we're measuring the resistance. So later on, after this, we have to calibrate and match the resistance with certain known load. And from there, compare at our force load on the actual buckling fixture.
Yeah, so the sensor just changed the current. So we will first calibrate it with known load and correlate what we'll be reading with a known load. So for example, we apply 1 Newton and see what that on the lab view. So from there, we'll know what load are we applying. Another test we have to do is torsion. So we picked a torque meter and a chart, and we design a fixture around it. So that's the torque meter and the chart. This is just a simple CAD representation of them. And these are brackets off the shelf. We cut them, thread them, and a plate, and strap the meter and the other fixture on the bracket. So basically, we put the sheath between the meter and here, and then the meter start applying torque. The meter can read torque and also can record it, so we know what torque are we applying. And again, we apply the torque until the sheath kink. So why we're doing it? To ensure that our design can withstand the torque the sheath will encounter in the operation. And we're gonna be testing between 0 and 45, and that's the normal twist angle that the sheath will encounter in the procedure as well.
So as Hazim mentioned, so the previous two tests, the buckling and the torsion test, so these are generally known as the performance tests. We want to test out real life performance of the sheath, how it would be tested in the scenario in which the doctor uses. The next fixtures we'll be making is the lubricity fixture, in which over here is the linear actuator. So you're going to have to buy it off the shelf. It's easier. And there's a the same force-sensitive resistor you've seen earlier. And so this vise is called a vise to hold a rod, and this vise over here is going to hold the catheter sheath. This linear actuator is going to push that rod inside the sheath. The problem is, right now we're trying to find a way to hold it tightly without actually collapsing on the sheath. So that's the fixture that we're making.
And what we're not showing here is one of these fixtures will hold the sheath, and one of these fixtures will hold a rod representation of catheter. And as the actuator pushes this bracket, the rod will go inside the sheath, and then the sensor will give us the force applied, what force we're applying to put the rod inside the sheath.
Ultimately, it has to do with what we're trying to design on our catheter sheath. So to characterize distance travel versus force, because the features may affect the lubricity, how smoothly the catheter goes in there, which is a problem. It can be a challenge as well to ensure that when the doctor take out the catheter, it doesn't pull the sheath out at the same time. So we need to ensure there's a smooth, lubricious surface inside the sheath, either through treating or design. So right now, all three tests, right, the performance test of buckling, torsion, lubricity, these will be done at San Jose State. The rest of the complicated tests, mostly for the biosafety and everything, we have to be outsourced, and we have to work with the company for that. Have them find another source for that. So these fixtures have to be built in the next few weeks. The introduced sheath will be manufactured over summer, so this will continue over the summer. We have to continue grinding over summer, and then test everything, test our sheath on the new fixtures. So right now the focus right now is kind of parallel. The designs have been sent to the company, haven't figured it out, and then right now on our side we're finish up the testing fixtures to get good data.
So this is just a simple cost analysis about the fixtures that we showed. Back-end fixture was the cheapest, $250. Because most of the parts are off the shelf, we only made the custom that hold the sheath on top. Torsion fixture is $1,500, mainly because the torque meter is around $1,300. Recipe fixture around 1,000. And this is market data for the sheath. So the TAVI procedure, which uses the sheath, is around 6 billion. And the sheath market itself is 360 million.
Not to mention if you remember earlier, the LabVIEW instrument earlier, requires a data acquisition device. We were using the device from previous years. The thing itself cost about $900. So that was, we did not have to pay for. These we paid for by the company, which was nice.
So future work, as Hoang mentioned, we will finish up building all these fixtures. The design are done. We just have to order and build them. Actually, the buckling fixture just arrived this morning.
Yeah.
So we're excited about that. We just have to order the other two and get the sheath manufactured and start testing based on the protocols that we developed. I would like to acknowledge our advisors and thank them for all the advices that they gave us during our journey. Dr. Selvaduray, industry advisors, Sabir Faryabi, Zandi, our professors, Dr. Ero and Will Stockholm. And I'd like to thank my partner, Hoang.
Sure.
Any questions?
So don't thank your partner. Because that's what I'm saying. I did all the work.
Right.
So try not to do it. So go back a couple of slides. So the future work. So are you guys designing processes to do these tests?
No,
that don't exist? Or the processes
no,
that
yeah,
exist?
you're right. Good question. We based off of already out there, some of the STM out there. The work that the torsion is actually done. There's a actual fixture out there that we can purchase the actual fixture, but instead of buying that, which costs about $10,000, we decided to do our own. So these most of these processes are out there.
So you look at the products that are out there, then you design them in CAD, then you order them from a particular vendor.
Yeah,
To suit your
we
needs.
build it. Yeah.
Yeah, so these are a combination between off-the-shelf and custom design. So for example, this one, all of it's off-the-shelf parts, and we only design in this piece, and then we build it together. Yeah. So we did combine all the CAD model and put them together. This one is actually everything on the shelf.
So is a 4-point bend test an accurate model, or are there actually a lot more bends in reality?
I'm sorry, I didn't understand.
You did the 4-point bend test,
Yeah.
right? Is that an accurate model for what you're trying to test, or will there be more pulses at multiple regions?
Yeah, so the sheath, when it's going to be in operation, it will encounter two forces, the hand of the surgeon and then where it's going to be fixed. So it's going to encounter two loads, as of suppose if we just applied one load in the center. So it's going to be more applicable to the catheter sheath.
I guess one kind of quick on your torque system.
Yeah.
Does that actually, it twists it as well? So it's providing both the actuation and the measurement?
Yeah.
That's why it's
Yeah,
expensive.
it is.
And then the other kind of quick question was, on your buckling, you have those, which scenario is your load, does this represent of all those buckling scenarios? What does your fixture do?
First one.
Is it 10?
Fixed
Yeah.
both
Okay.
that, yeah.
Because both are fixed. The adapter that we have, go back to the picture. The sheath will go inside this adapter. This adapter is composed of two cylinders that goes threaded together, and there's a gap in between. So the sheath will go inside this part here.
Okay.
And
So,
then-
can I see that again then? The other, you said that was the fix, that's a pin condition. Are you sure it's not the second one?
Oh, no, sorry, yeah.
Yeah, sorry.
Fixed, sorry.
Fixed condition.
Okay.
We'll fix both ends.
Okay.
So hold it forward and then
And then,
That's right. This is pin that has rotation.
so just with that, your material is, what are these catheters made out of, or these sheaths made out of?
There's multiple materials. So this one is Amarlix, is HDPE. There's PBAX. There's also a composite.
So these equations assume the material is linear elastic, yeah?
Linear.
Linear elastic materials, is what this assumes, what if you're gonna use E?
Yeah. So
Is
this
that-
is
is
the
that-
elastic modulus.
Is that a valid assumption for these materials?
Like what's the main concern that you had?
Are the materials linear elastic? If you stretch them and then like go.
Oh,
do
the
they bounce
elastic,
out?
yeah.
Are they elastic?
The material we're using, yeah, it's actually an elastomer. Yeah, so,
We have to,
Double check on that.
yeah, I'll have to check on that.
All right, we'll stop there for now. Thank you very much.